Hello, everyone, and thank you for joining us. And we're very excited to be here. So first, I will introduce myself. My name is Kinneret Raviv. I am a principal. Yeah. Okay. Okay. So my name is Kinneret Raviv. I'm a principal software engineer at Akamai. I have more than 8 years of experience with big data technologies. Today, I work mostly with Spark, and I also worked in the past with Hadoop and MapReduce. Nir is the principal performance engineer in our group, and he will talk in the second part of the session. We will start with an overview, and then we will talk about a custom data source that we've developed in our group. Then we will talk about a performance tuning we did and some GC analysis. So about Akamai, our company. Akamai is the largest CDN service provider. It's also a cloud security solutions company. Our customers' website traffic is passing through more than 300. 1, 2, 3. Hello, 1, 2, 3. Okay. So our customer website traffic is passing through more than 350,000 servers that distributed globally. In Akamai, we have more than 8 billion requests per day. And Akamai counts more or less 30% of the internet traffic, of the global internet traffic. So our biggest challenge here is that we're dealing with a massive amount of data. So about our group, CSI, so part of our customer traffic is also a malicious activity, and we have the ability in Akamai to detect this activity and to send security events logs to the CSI platform. So CSI platform is collecting, analyzing, and distilling quality security intelligence information. Our incoming traffic is about 6 gigabytes per second. Is about 100 billion events per day. So our product, based on those security events, the customer can define alerts. So the product triggers alerts based on these security events according to the definitions of the customer. So here we have an example of an alert that the customer was defined. We have here a time series with the blue bins are security events, and the pink bins those time windows which this alert was fired. So about our technical architecture, those security events log are saved in a blob storage in Azure format and Kafka. We will dig into it later. The processing itself is done in real time using Spark structure streaming on top of Kubernetes. And the output is saved as a text file on blob storage that contains all of the alerts that was detected on each macro batch. So let's talk about the Spark data source we've developed. So as I mentioned before, our security events log are stored in the on blob storage in the Azure format. The reason we can't read directly from the blob storage is that this blob storage also contains corrupted data of failed transactions. So we have also a Kafka topic that contains a topic with messages. Each message contains a path to a validated data file and a metadata about this file, like size and number of records. So our data source is kind of combination of the Kafka and the blob storage. So let's talk about the Spark data source API in general. The data source API gives the ability to read data in a distributed way. We have standard built-in sources in Spark, like per K and JSON. We have also third parties that were extended this API, like Cassandra. We also have the ability to develop our own custom data source, like we did. And this is the name of the data source, Kafka Blob Data Source. Okay, so in order to develop a data source, we need to implement several classes. Here are the relevant part and the main part that are relevant to this session. So first of all, in the driver level, we have the table provider. The table provider is kind of declaration in front of Spark that this is a Spark data source. Then we have the microbatch stream class. In this class, there is a method, plan input partitions. This method is executed in each iteration and plans the partitions of the current macrobatch. Then each partition is executed as a task in the executors, and the executors level, we have the partition reader that reads the actual data from the blob storage. So let's take a look in our implementation of the plan input partition. So first of all, we have a Kafka consumer in the driver that initialized while the streaming is started. Then, in each iteration, we poll messages until one of the following conditions is met. If we're in a catch-up mode means that we have a high Kafka leg, then the consumer poll messages until the total and summarize the size property in the message until we met the maximum desired memory for a macrobatch. If we're in a regular mode and we don't have a high Kafka leg, so we poll messages until the queue is empty. So the first optimization we developed here is to filter out messages that are not relevant to the application anymore, like TTL. That gives us the ability to filter data in the plain level and then saves I/O later in the executors. Okay, so we poll the messages, and now we have a list of messages that each message contains a path. Now, we need to divide the list between partitions, then each partition will execute it as a task. Now, we need to choose the right strategy, the right partitioning strategy to the use case. So the goal here is to plan the partitions to achieve efficiency and to avoiding data skew. So the most simple partitioning strategy is to assign a partition to a file. That means that the number of tasks will be the same as the number of files. And that means high number of tasks. The second strategy is to assign multiple files to one partition. We retrieve the desired partition size from the user and then iterate the list and divide the files between the partitions, and we get partitions in the same size, more or less. That means that the number of tasks is not fixed between iteration, and that can cause, that means that the resources are not fully used. For example, if in the single micro batch, we have 500 single partitions in the same size, 500 partitions in the same size, but we have only 400 available cores. That means that 400 tasks will run in parallel, and then 100 cores will run in parallel, and 300 cores will rest. So the second strategy we use is to divide the files according to the desired number of tasks that was provided by the user. A user can provide to the data source configuration in the option. So here we iterate the list and then divide the files between the desired number of partitions. And we do it in a smart way. Not all the files are in the same size, so we have algorithms that balance between the number of files of each partition and total size of the partition. Another challenge we have, so those security events logs are saved in the single storage account, and we have multiple products that read from the same storage account, and sometimes we have throttling errors. So in order to reduce them, reduce the parallelism while we don't need it. So when we have a high Kafka lag, so we tell the data source, okay, so increase the parallelism and use as much resources you can. But if we are not in catch-up mode and we don't have high lag, we can use less parallelism and then reduce throttling errors. Okay, so summary for those of you who plans to develop a custom data source. So first of all, data skipping. Try to read only relevant data in the executors. We did it, for example, with the TTL feature. We filter out messages that was expired, that is not relevant to our use case anymore. Also, try to plan partitions in size as much as, in the same size as much as possible in order to avoid data skew. Also, the data source API provides a multiple interface optimizations interfaces, like push-down aggregations, push-down filters, and push-down and column pruning. So if your source supports those optimizations, it's highly recommended to also to implement those interfaces. Okay, thank you. This was my part, and now Neil will continue.
In the second part of this session, we're going to talk about performance tuning and GC analysis. My name is Nir, and I'm a principal performance engineer working at Akamai. Reading the data from our data source is considerably a heavy phase in our application. In every micro batch, the application is reading approximately 100 gigabytes of uncompressed data, split it into thousands of files in different sizes. When we started to tune this phase, we decided to use all the available cores in our applications, which is 400 cores, as the number of partitions. The result that we got is that the total read time was approximately 12 seconds, and the spread of the results was relatively wide, although the connector was trying to balance the amount of data in each partition. Next, we decided to double the amount of partition to 800, even though we knew that not all the tasks are going to run on all the executors at the same time, and that's because we only have 400 cores in our application. We decided to use 800 partitions. In that case, the total read time decreased to 7 seconds, and the spread of the results was significantly better. Followed by our success, we decided to increase the number of partitions even further to 1,200. In that case, although the total task time was better compared to the previous step, the total read time was a bit higher, and that's because of the overhead of scheduling more tasks. To sum it up, creating smaller balanced tasks by increasing the number of partitions we use to be 2 times the number of cores we have in our application helped to reduce the read time by almost 50%. Now, let's talk about garbage collection. How many of you enable garbage collection logs in your Spark applications? So to enable garbage collection logs in your Spark applications, you simply need to add the JVM arguments listed here to your driver and executors based on the Java version that you're using. Once you've got those logs, you can analyze them using multiple tools. My personal favorite is GC Easy, which provides great visibility of what's going on inside your application, and I'm going to show some examples for it. In this image, we can see certain metrics that are related to throughput and latency. Throughput is the amount of time your application is doing its own logic out of the total time, which includes garbage collection time. The higher the throughput is, the better. As for the latency, we can see metrics that are related to the average post-GC time, the max post-GC time, and the breakdown. Next, we can see a time series graph of the post-GC duration time. This can help us to correlate issues that are related to high post-GC time in our application. In this example, you can see that the frequency of full GCs is increasing, and the pause time is increasing as well, and this can cause stability and performance issues in our application. In the last example, we can see the heap usage after GC. In the first image, we can see that the total heap size is bounded, which usually means we don't have any memory leak. In the second image, we can see that the total heap size is growing, which usually means we have a memory leak. In order to understand what is causing the leak, we will have to take heap dumps and analyze them. And now I'm going to talk about garbage first, which is also known as G1. So G1 is the default garbage collector starting Java 9. You can enable it in previous Java versions by adding the JVM argument listed here to your driver and executors. Before G1, the heap was structured into 3 sections: the young generation, the old generation, and the permanent generation. Every memory object ended up in one of those regions. G1 has a different approach. The heap is partitioned into a set of equal-sized heap regions. Certain region sets are assigned with the same roles as in the older collectors, but they don't have a fixed size. This provides great flexibility in memory usage. When G1 works, it executes the concurrent global marking phase to determine the liveness of objects in the heap. After the mark phase completes, G1 knows which regions are mostly empty. It collects from those regions first, which usually yields in a large amount of free space. And that's why this method of garbage collection is called garbage first. When we used G1 in a very similar application to what we have today that was running on Java 8, we had to tune many parameters to get to the throughput that we wanted. This is just an example. When we use it in Java 11, we didn't have to tune any parameter to get to the throughput that we wanted. This is because G1 was improved in newer Java versions. One of the major improvements was that G1 can perform full GCs using multiple threads. Before that, G1 used a single thread to do full GCs. So if you can improve upgrade the Java version that you're using in your application, you will probably gain a performance boost. So here's a short summary of what we've talked about. Adding garbage collection logs to your Spark applications is very simple. All you have to do is add the JVM arguments we've seen before to your driver and executors. Analyzing your GC logs can help to identify memory issues. When you're analyzing your GC logs, pay attention to those 3 important metrics. The first one is the throughput, which indicates how much time your application was working out of the total time. The second one is the average and max GC post time. And the third one is the heap size after GC, just to make sure you don't have any memory leak. And last but not least, G1 is more flexible in terms of memory usage compared to the older collectors. So consider using it, especially if you're running on Java 8, Java 10 or above. Thank you. Any questions? If the amount of partitions is fixed, I assume that it really depends on the use case, but having the same number of cores to read in parallel might give you the best results, because that's like the most parallel you can go. If you can make it dynamic, and then you can split it into smaller chunks, and then you can see.
Okay, thank you.
Okay, so how do we decide about the resources, the amount of resources? Yeah, so first of all, the most important thing that it will work well in a catch-up mode. So we tested the amount of resources against our desired total memory, maximum total memory per micro batch. And then we do tests, and we wanted that the rate of reading the data will be less than the rate of the incoming data, and this is the number we achieved. No, we're not checkpointing the Kafka offsets. We let Kafka manage our offsets, but we do validation in each iteration that we don't have overlap between iterations, that we will not have data duplications. No, the offsets are managed in Kafka, not in the consumer. We have a group, a consumer group that is saved in Kafka, and Kafka knows where is the pointer of this specific consumer group. So we let Kafka to manage the position of this specific consumer group, and in our side we do validation. In case of failures that between the writes and the commits and so on, that we won't have duplications.
Thank you.
Okay, so there is several scenarios in case of failures, okay? The question is the timing of the failure. If it's the middle of the write, so there is no Spark commit at all, and we're fine. If the write was completed, then Spark has in the checkpoint directory, Spark save a file that indicates that the microbatch was finished successfully. So in our validation, we have a kind of logic. We check the Spark commit, and we compare it to the offset we saved locally and the offsets that are saved in Kafka. And we do the calculation to see if the previous microbatch was finished successfully with that commit or not. So, okay. Thank you.
Thank you.